So imagine that we're in 3D, and I'm just going to say to some degree that, the good news is you already know how to deal with like 99.999% of all the tensors you'll ever meet in your life. That remaining, 0.01% are super important. And in fact, everything is a tensor in some sense. So remember, we demystified or rephrased vectors themselves as a vector is anything that transforms in the proper way. Scalars all transform in the proper way. And what we're going to do now is we're going to say that this is actually what's called a rank 0 tensor, because it has one component. A scalar is just one number. And 1 is 3, the dimension of our space, to the 0 power. Okay, and the important thing is that it transforms properly. A vector is a rank 1 tensor because it has 3 components in 3D, and that is 3 to the 1. And it's a true vector. You can write down 3 numbers, and if those 3 numbers are defined through a cross product in a left-handed coordinate system or something like that, yeah, it's 3 components, but it doesn't transform properly. So before you get to be a proper vector, you need to transform like a vector. So that was, what we did on literally the first day of this class. So we transform properly. Okay. Now this is the thing that might be a little bit new. What is a matrix?
Probably depends on the matrix, because you can have like any number of components.
Yeah,
depending on what you're representing. Yeah,
you didn't fall for my really feeble trap. Okay, let's say I have a 3x3 matrix that has A11, A 12, A13, A33. So it is a 3x3 matrix. What might I call it? So we're not quite there yet.
Call it a rank 2 tensor.
Yes, so this is a rank 2 tensor because it has 9 components, which is 3 to the 2. Okay, but not every box of 9 numbers in a 3x3 format is a rank 2 tensor. So this is actually going to need its own transformation criteria. And this star doesn't mean complex conjugate. This means 3x3 matrix that transforms properly. Okay, so does anybody have an example of a tensor from physics? I think you may have seen 2. So what we haven't shown is how you transform like a tensor. Okay, you may have seen the inertia tensor, but I don't want to do that one because it's, I think, like less intuitive because it transforms, doesn't even transform vectors, it transforms pseudovectors. So let's talk about the stress tensor. And let me take like a little box of stuff, right? So we're not putting forces on point particles, we're putting forces on an actual, real thing. So clearly there's more than a vector's worth of force on this. So I can have a force that points in, this direction, and it could be acting on the top surface. Call it Ft, I don't know. And then I could have a force that points like this on the right surface. And then I could have a force that points like this on the front surface. That's gross notation, but you kind of get the point. So what I can do is realize like, okay, maybe I can parse for this block of stuff, this like delta tau volume. I can ask about the forces that are acting on each of the surfaces. So we want force on an arbitrary surface. And we'll call it df, because we're gonna, maybe eventually get a continuum and shrink our sizes, our volume to 0. Want force df on some surface. And how do we describe surfaces in this class? Or, not just here, but everywhere properly. So surface is described as, I got a magnitude, but I also need to tell you the direction, so normal to that surface. So this is a vector too. So this is the game that all of a sudden, when you're talking about stress on a continuum or an actual finite sized object, this is the game you have to play, is vector goes in, vector goes out, right? What is the most generic thing that transforms one vector into another vector? So which is to say, what type of mathematical object most generically goes here?
Some kind of cross product or something.
Yes, cross product. So cross product turns out to be a pseudo tensor because it makes pseudo vectors, but that's one example of doing it. And you can represent the cross product by a 3x3 box. Okay.
Or maybe just a scalar.
Say again?
Or maybe just a scalar in this case.
Yeah, so you could try a scalar, but a scalar, for instance, if I look at this force that I drew, which I drew kind of like deliberately, there's sigma top. That's always normal to the surface. If this was just a number, what would always be true about the orientation of sigma and f? So they would always, I would just stretch or shrink it, right? They would always be parallel. So generically, what I need to do to get from some oriented surface to get a force that might be perpendicular to that or have a parallel component is this needs to be a 3x3 matrix. So technically, because it's got to transform the way the vectors transform, it's got to be a rank 2 tensor. And to write it out, because this is stuff that's kind of difficult to visualize sometimes, we'll call it dfx, dfy, dfz. The most generic thing that I could do is write something that looks like this: sigma x, sigma y, d sigma z. So I'll call this txx, t xy, txz, tyy, tzz, tyz. Okay. Once and only once. Oops. Tzzy. Tyz. God. Had it and then I screwed it up. There. So this is the way that I get from one vector to another vector most generically. If those two vectors that I'm transforming in between are truly speaking vectors, which is to say they transform correctly, obviously this thing needs some similar transformation properties. So this is what's called the stress tensor. And if you squint at it, you can kind of see what it means in some sense, is that the diagonal components tell you the force that's trying to compress or stretch the box, right? So it's pushing an x component, pushing directly along an x component. And then these ones along the sides are they are called shears. So they're trying to maybe introduce a tangential component, right? So this is how I get on the x component, for instance, something that, or on the yeah, on the x component, something that pushes in the y direction. So it's this and this. So that is a tensor. It's got to transform properly. And if you look at it, it's got units of newtons per meter squared if you express it in whatever coordinates. So does that make sense? Okay, we have time for one more example. Unless you guys know it, you may have seen it or just think for a second. What is another case in physics where I have vector in, vector out? Think about the end of mechanics, everybody's favorite part of mechanics. And they told you it was a number and you had to look it up in a table and they lied to you.
Is it the spring constant?
So you can define, and that might be what you guys, I don't know if you skipped that chapter. So you can define elasticities in the form of a matrix. And those would describe the material properties of like some stretchy stuff, like a property. So that is absolutely a tensor. So you could talk about elasticity as a tensor. Yeah, I don't remember the definition offhand, so I'll go fishing for another example.
I was going to
yeah,
say
so that
moment
one,
of it.
yep.
Sorry.
Yep,
Moment of
so
inertia.
exactly, inertia.
Yeah.
So Young's modulus, if you have an anisotropic material. So if you remember Young's modulus, we kind of defined like as an analogy of a spring. So let's say that you have like some stretchy stuff, right? And you realize this is a force and the deformation that I could put on this is also a direction. So this is R. Again, you would have something like this. I forget its typical name, but you could have a elasticity tensor. Absolutely. So, oops. I just don't remember like offhand what the generally accepted definition of a notation for that is. So I won't use it as an example. But yeah, inertia tensor also has these properties because I have a thing and I'm going to rotate it, and my angular velocity, so we're using omega twice for two different things in this class today. Sorry, but that's physics. This is technically a pseudo vector, but this is a vector that describes the rotation. And I might ask about the angular momentum, which is also a vector. The reason these are pseudo vectors is because you had to use your right hand, so there's a degree of arbitrariness. And then what you were told is that L equals I omega was the analogy of P equals mv because angular velocity is like velocity, angular momentum is like momentum, and moment of inertia is the thing that's like mass. Okay, but what's the most general way of getting from one vector to another? It's a tensor. And I know it's a tensor because there's no single value for I. Like something doesn't leave the factory with I, the moment of inertia, stamped on it. And if I rotate it around this axis versus that one, or heaven forbid, I rotate it around this axis, this is going to be much more difficult. So the angular momentum depends on which axis you're choosing. And L equals I omega is actually a tensor formula. So this is Lx, Ly, Lz, and this is Ixx, 9 by 9 box, omega x, omega y, omega z. And instead of, this is why you got to look something up in a chart in physics. It wasn't because we like you. It's because this is the formula for the kj component of the moment of inertia. Integral over the volume, the density of the material at that particular point, and then your friend Kronecker delta kj r squared minus the kth component, the jth component, so the off-diagonal bits, delta tau. So it's a volume integral over the density of the material with the Kronecker delta to get you from the diagonals to the off diagonals. So you skipped out on that for now, but it'll come back into your life in at the end of what is it, 3810, whatever what advanced classical is. Okay, so any questions about any of that? Okay.